Hello everyone, I'm going to present our work, Promoting High Diversity Ensemble Learning with Ensemble Bench. We have already open sourced Ensemble Bench on the GitHub. Here's the outline. So what is high diversity ensemble learning and why do we need that? In the meantime, there are also several open challenges. I will answer these questions, use a case study on 8 machine learning models. Then I will introduce Ensemble Bench. It includes a set of ensemble evaluation metrics, the Q diversity matrix, and the enhanced FQ diversity matrix. It also includes a set of ensemble consensus algorithms, such as soft voting, majority voting. And last, I will introduce the architecture and the workflow of Ensemble Bench. Let's first have a look at ensemble learning. Ensemble learning has been an active research area in machine learning domain for over 30 years. It follows these steps. First, we need to obtain diverse base models. There are many ways, such as using different subset of data, using different hypermeters, and even different learning algorithms. Here, if the base models are obtained with the same learning algorithm, such as SVM or decision tree, we call it homogeneous ensembles. If the base models are obtained with different learning algorithms, such as SVM, decision tree, and neural net, we call it heterogeneous ensembles. Of course, we can also use different pre-trained models to form ensemble. Then, we need to combine these base models together to form an ensemble team, such as the ensemble with all the M base models. Then, we need to perform ensemble consensus by using soft voting, majority voting, or plural voting, etc. There are actually two ways to get an ensemble. Consider a base model pool of M base models from F1 to Fn. The conventional approach, as I mentioned in the previous slide, is using the ensemble of all the M base models, represented by AdaBoost, Bagging, and Random Forest. The second approach, we call it Ensemble Bench. We prefer to use ensemble teaming from any K model, the subset of M base models, to form ensemble team, as long as K is larger than or equal to 2. So what will happen with ensemble teaming? Let's still consider the same base model pool. The number of candidate ensembles can be calculated as following, with team size S varying from 2 to n. For each S, the number of candidate ensembles is equal to a selection of S models from M base models in the pool. Therefore, the total number of candidate ensembles is about 2 to the power of m. This number grows exponentially with m. However, the performance of different ensembles varies a lot. For example, on ImageNet, the ensemble accuracy is ranging from 61 to 80%. Therefore, it's a non-trivial problem to select high-performance ensembles. For example, m equal to 8, 10, or 15, we can see the total number of candidate ensembles grows exponentially, especially when m equal to 15, we have over 32,000 candidate ensembles. There are several open questions. First, could a subset of the M base models as an ensemble outperform the ensemble of all M base models? Second, are there more than one high-quality ensembles? And if so, how to find them? These questions can be answered with a case study on 8 machine learning models. This figure shows the decision boundaries of these machine learning models. With 8 machine learning models, we have 247 candidate ensembles in total. Here is the experimental setting. It's a binary classification problem. We also show 2 example ensembles on the last 2 columns. One is the ensemble with all 8 machine learning models, denoted by all, and another one is the best candidate ensembles among the total 247 ensembles. We can observe that different machine learning models perform very differently. This table shows the prediction accuracy comparison of base models and ensemble teams. 3 observations should be highlighted. First, the ensemble of all m equal to 8 models may not be the top performing ensemble, the best ensemble. and may not even outperform the memo model with a maximum accuracy F3. Second, ensemble teams without the top-performing base model F3 may still obtain high accuracy, even better than or equal to F3. Third, some ensemble teams can outperform individual memo models, and others may not. So it comes to the question how to evaluate ensemble teams. We argue high-quality ensembles should be able to improve the prediction performance over every memo model, that is accuracy larger than or equal to Mmax, the memo max. For example, the ensemble team of model 0, 1, 2, 3 achieved ensemble accuracy of 92.75% versus the maximum memo model F3 with accuracy 92.5 on dataset 0. In the meantime, some high-quality ensembles could improve the prediction performance over every base model in the pool, that is accuracy larger than or equal to Pmax, which is a higher standard. In order to evaluate ensemble selection algorithms, we also propose ensemble accuracy range, average ensemble accuracy, and standard deviation of ensemble accuracy of the selected ensemble teams. This table shows the ensemble evaluation example. From this table, we can also observe that the percentage of high-quality ensembles among the total 247 candidate ensembles are below 30%. So the answers to the above two questions are yes. Next, we have another two questions. First, are there good ensemble diversity metrics helpful for identifying and selecting high-performance ensembles? Second, what quantitative metrics are informative measures for evaluating and comparing alternative ensemble teams? Ensemble diversity is a property that captures the relationship among the memo models of an ensemble team. An ensemble team with high diversity should be able to complement one another and have high agreement on positive examples, while all the memo models make the correct prediction. In the meantime, they should also have very low agreement on negative examples, while one or more memo models make wrong predictions. The low agreement on negative examples also means high uncorrelated error rate, which leads to low negative correlation and higher failure independence. Therefore, high diversity ensemble teams are expected to have better prediction performance. In the literature, there are several diversity metrics measure the level of disagreement among memo models of an ensemble team. We call them Q diversity metrics. They were introduced to validate and interpret how good an ensemble model is, such as a model from random forest or AdaBoost. For pairwise diversity metrics, they will be calculated by using the average over all pairs of memo models, such as Cohen's kappa, Q statistics, binary disagreement. For non-pairwise diversity metrics, they can be calculated directly on a group model, such as Fleiss's kappa, Kuhaiwi-Warpert variance, and generalized diversity. Here's a definition for pairwise Q diversity metrics. This slide shows a definition for non-pairwise Q diversity metrics. For using Q diversity ensemble selection, we can first calculate the diversity scores for each ensemble team in the candidate ensemble set, ENS set. Then, we can calculate the average diversity score as the mean threshold. The ensemble teams that have lower diversity scores than the mean threshold with higher diversity will be selected. We then show an example on ImageNet for using Q diversity ensemble selection on the table. We highlight three observations. First, compared to baseline, QKW, QGD improve the lower bound of ensemble accuracy of the selected ensemble teams. Second, QGD also improves the average ensemble accuracy of selected ensembles. However, 5 out of 6 Q metrics resulted in slightly worse ensemble accuracy range and average ensemble accuracy. What we have learned from previous example is that Q diversity metrics are not good ensemble diversity measure for selecting high-quality ensembles. The following 3 figures shows that we cannot find a consistent relationship between ensemble accuracy and ensemble diversity. Therefore, we further propose FQ diversity metrics to improve the existing Q diversity metrics. Here's the intuition. Focal or target model is motivated by mitigation strategies against adversarial attacks on the target victim model. In our group, we have some ongoing studies to use ensemble for defense. Ensembles of equal number of member models, that is of equal size, and share the same focal model tend to show a clear correlation between ensemble diversity and ensemble accuracy. Combine these 2 points, they both improve the quality of using negative samplings to capture negative correlation among member models of an ensemble team. Therefore, our FQ diversity metrics use focal model and focal model driven negative sampling to sample negative samples, and then we compute ensemble diversity on these negative samples. We call it focal model driven diversity computation. With the computed diversity scores, we can perform ensemble selection and pruning with adaptive learning of diversity threshold instead of using the fixed mean threshold. Due to space and time constraints, for the details, please refer to our technology report. In the meantime, Ensemble Bench also supports other optimizations like EQ diversity metrics and some other filters like alpha filters to preemptively prune out some low-quality ensemble teams. Here are the base model pools we used in this study for Cephir-10 and ImageNet, these 2 benchmark datasets. We then revisit the negative sampling used by existing Q diversity metrics. The above 3 figures shows a case of using negative samples from any model or all models. We cannot find a consistent relationship between ensemble accuracy and ensemble diversity. The 3 figures below shows a better case of using the negative samples from a specific focal model and also restrict the ensemble team size as equal to 5. We can observe that focal model-based negative sampling with a fixed team size shows a clearer correlation between ensemble diversity and ensemble accuracy. We then showed 10 example ensemble teams on Cephir-10 and ImageNet. We found having the top performing base model 0 for Cephir-10, 5 for ImageNet may not guarantee high ensemble accuracy. In the meantime, FQGD has high correlation to ensemble accuracy compared to QGD. We further perform the experimental comparison on ImageNet by using Q, FQ, and EQ diversity metrics. The EQ diversity metric combines the 3 top performing FQ diversity metrics to further improve ensemble selection. We highlight 3 interesting observations. First, FQ has higher probability of choosing top quality ensembles with ensemble accuracy larger than or equal to member max. The percentage is close to 100% for FQ, BD, KW, and GD. Second, the ensemble accuracy of ensembles selected by FQ are more stable than Q. That is smaller standard deviation of ensemble accuracy. Third, EQ achieved the highest average ensemble accuracy. The takeaway from here is that FQ and EQ metrics perform much better than the baseline and Q metrics in terms of high-quality ensemble selection. We then need to consider ensemble consensus algorithms. For this part, due to the space limit, please refer to the full version of this paper on arXiv. The popular ensemble consensus algorithms include soft voting, that is model average, majority voting, and plurality voting. We further propose Bayesian voting for comparison. The voting principle is that we can use prediction vote or prediction confidence of each member model and combine them to get better prediction results for an ensemble team. The soft voting will output a prediction vector that is the simple averaging of the prediction vector of each member model. Majority voting will output the class received the majority of the votes, that is more than half. For plurality voting, it will output a class received the highest number of votes. However, these voting methods will assume equal votes for each member model. We further propose Bayesian voting to learn the weights for each member model and then perform weighted soft voting with a learned weights. Here's a pseudocode for each training sample and for each member model. If the model Fi makes a wrong prediction, its weight will be penalized. For each training sample, after finishing adjusting the weights for every member model, the weights will be normalized to ensure the sum is still 1. Then, with a learned weights for each member model, we will perform the weighted soft voting to get the prediction results. This table lists a few example ensemble teams selected by the EQ diversity metric. To compare these 4 ensemble consensus algorithms, we found all of them have reasonable consensus performance on the selected high diversity ensembles. In the meantime, soft voting and Bayes voting work slightly more effective for the 2 base model pools used in this study. This figure shows the framework architecture of ensemble bench. It consists of 7 functional components. The base model procurement module is responsible for collecting base models and managing base model pools for given dataset and learning task. The candidate ensemble formation module will form ensemble teams of different team sizes with different focal models. The negative sampling module will generate random negative samples for specific focal model. Then we can perform ensemble diversity evaluation with different diversity metrics. With the calculated diversity scores, we can select high diversity ensemble teams by using the mean threshold filter, alpha filter, k-means filter, and even hybrid filters to obtain the set of good ensemble teams. Then we can perform ensemble consensus algorithms to get the final prediction result. Ensemble bench also supports diverse ensemble recommendation. In the current release, we simply use a random selection over the set of good ensemble teams. Ensemble bench provides systematic approaches for selecting high diversity ensembles. Compared to conventional ensemble learning, we added another steps to form ensemble teams of different sizes and then perform ensemble selection to select these high diversity and high accuracy ensemble teams. In the meantime, we also provide a set of metrics for assessing the quality of ensemble teams in terms of prediction performance. We also provide a set of metrics for evaluating the quality of ensemble selection approaches. To summarize, we introduce a set of quantitative metrics for assessing the quality of ensembles and for comparing alternative ensembles. Ensemble bench implements a suite of baseline diversity metrics and optimized diversity metrics for identifying and selecting ensembles with high diversity and high quality. 4 representative ensemble consensus algorithms are provided in the first release of ensemble bench, enabling empirical study on the impact of consensus methods on ensemble accuracy. Here's a reference. Thank you for listening. Feel free to ask questions.